Hello, everyone. Thank you for your kind introduction. And I'm here with my colleague from AbbVie, Shashank Shekhar, to give a presentation on automation and information management impact at AbbVie to accelerate process development and manufacturing. And I really want to thank Mettler for giving us an opportunity to come here and present on this webinar. So, with I would like to start my presentation with this outline. We're going to start with AbbVie automation strategy. So we're going to talk about what it took for us to build this multi-year vision and strategy to build this end-to-end automation infrastructure. And then we'll move into various platform technologies. We'll start with high throughput experimentation. And we'll talk about various application of those technologies on catalytic reaction, organic reaction, and solid state chemistry. Then we'll move on to the second platform, which is more around data-rich experimentation workflow for process design and optimization. And we'll wrap up the presentation with the last platform, which is custom-built automation, which we believe is a unique infrastructure we have at AbbVie, and we'll talk about more in next few slides. So here is the AbbVie vision on automation. We want to really transform the culture and the way we do research to enhance safety, access new enabling capabilities, and gain process development efficiency with high quality data through a deliberate and sustainable automation competency. And here are some of the deliverables of this multi-year vision. We want to establish a cross-functional team to develop and execute this strategy, facilitate the widespread adoption of automation across the organization, identify and exploit the breakthrough opportunities, and lastly, we want to research and develop custom solutions. So some of the key strategic elements which really worked out for us, we started with establishing the focus team with dedicated team members to each platform for nurture, care, and accountability. Then we had top-down accountability in setting expectation to use platforms for each of the project. We wanted to realize the full potential of existing platforms which we have already, such as Mettler, Quantos, solid dosing robot, Solubility, and all the technologies we're going to talk about in the next few slides. We also realized that in order to gain momentum across the organization, we really want to leverage our quick wins as a proof of concept and extend those to the wider organization in a sustainable manner. And we want to make sure there are no silos in the organization. Each of those platform technologies are supported by a highly cross-functional teams, and we'll talk about that in the next few slides. And lastly, we want to identify and develop working relationship with various automation providers, such as Mettler in this case, which really helps us to gain momentum. And we want to really make sure that we are deploying off-the-shelf solutions where it's possible. So in this slide, I'm going to talk about the four platform technologies and dedicated teams we have for each of these, starting from high throughput experimentation. This particular platform is mostly to parallel screen and optimize and develop the novel chemical transformation and solubility and polymorph screening. The next one is medium throughput experimentation. Once the discrete variable screening is completed through high throughput experimentation, we would like to do continuous variable screening using these medium throughput experimentation platform. And here the idea is to parallelly screen and design and optimize in number of experiments less than 24. And here the PAT plays a significant role to enhance our process understanding. The third platform is the custom automation. Here, when there is no off-the-shelf solution, the off-the-shelf solution highly complex or cost prohibitive, we would like to build our own custom solution and to satisfy unique process development needs. And we'll go into a little more detail. Now, each of these teams, as you can see, can generate tremendous amount of data. So we have a dedicated team, which is an information management team, to support these three teams and produce actionable insights and integrate our data solutions end to end. So here is the overall automation workflow for the process development. As some of you may know, the typical project starts with identifying the chemical transformation. Then we move on to distinguishing and prioritizing the hits, then optimize and design the nominal process. And when that process is ready, we assess the scalability of and developing the robust process and then ultimately execute at the large scale. For identifying the chemical transformation and distinguishing the prioritizing hits, mostly high throughput experimentation to screen discrete variables such as reagents, solvents, temperatures. Those are the ones which plays a significant role. And then we move on to the optimizing nominal condition, where we want to screen the continuous variables such as reagent equivalents, orders, rate of addition, temperatures. And there, the major platform we have is the Mettler Platform. We use that to further develop the scalability of the process, defining the limits and evaluating where the process can fail. And once the scalable process is ready, we execute the process in our pilot plant at large scale. Now, some of the needs can be managed by these high throughput and medium throughput experimentation platform, but there are some times where we have to develop our own custom solutions, and information management team and custom team can support wherever we have those gaps. So this is the last slide of my presentation. These are some of the other essential elements which you really need to focus on to leverage these automation technologies. So the first is the resources. You need to have the right resources with the right skill set, and we need to continuously give the development opportunities to these resources to make sure they are excited and developing these new technologies and bringing the right skill set at the right time. And the third one is the culture. We need to create the culture of sharing and between different teams and different projects. So in our opinion, these are the three major elements which needs to be at the right place to leverage these automation technologies. And lastly, in addition to gain efficiency and develop quality data, we have found out that these automation technologies really enabled us to get key insights and get us enable processes which was not possible with such manual screen and manual process development. And this is, in our opinion, is a major selling point for establishing this automation workflow. And lastly, with automation, the idea is to impact the decision-making process earlier on the project with more knowledge and with the less material. With that, I would give it to Shashank, and he will talk about some of the technologies he has developed in high throughput experimentation.
Thank you, Moez. Our HT effort within process chemistry started in the center of catalysis, but is rapidly expanding into other non-catalytic reactions such as amide coupling, SnArs, as well as solid-state chemistry. So within the center of catalysis, we work on metal and enzyme catalyzed reactions as well as reactions under pressure. And the group is very well supported by state-of-the-art HT equipment as shown here, as well as a group of very enthusiastic colleagues, again shown at the top of the slide. Our motivation to use HTE is to gain efficiencies in our process and to find non-obvious solutions which are hard to get by. So we strive to address the early discovery problems within a week, FIH scale problem within 2 weeks, and we are willing to spend up to a month on developing a commercial process. So we really want to develop the optimal solution as soon as we get our compounds in our hand. And there are clear benefits to that because this means that minimal optimization is required as the project or the program moves forward. However, we definitely don't want to spend more resources or time as outlined above on these slides. So let me give an example of the benefit of this finding optimal solution. So our project team was working on scaling up the Negishi coupling shown here. So reaction between bromopyridine and cyclopropyl zinc bromide in the presence of a palladium catalyst. So the reaction conditions shown here were used to scale up a related compound on 50 kilogram scale. So we were reasonably confident in these conditions. So as you can see, the coupled product was obtained in high yield, more than 90%, but it came along with 2 to 3% of difficult to reject dimer impurity. So what it meant that if a solution was not found immediately, then column chromatography will be required for FIH campaign, which is not ideal. And which also meant that if we had to revisit this reaction for later scale up, then we'll have to re-optimize these reactions. So as an organometallic chemist, I have been taught to think about factors that enable the formation of major product, but I find it really difficult to pinpoint to parameters that control formation of trace levels of these impurities, such as the dimer shown here. So because of our infrastructure and the workflow we have put together for HT work, a solution was found within 2 weeks within our goal that not only formed the coupled product in similarly high yield, it reduced the dimer impurity to only 0.3% level, which was acceptable even if we could not reject it, that's okay tox wise. So what it meant that no column chromatography was required for the FIH campaign, and as you can see, the palladium loadings are actually even lower than the conditions that were used earlier. For it meant that the project team feels comfortable on scaling up these reactions on larger scale. In fact, they have already scaled up this reaction to at more than 50 kilogram scale. So we found the optimal solution pretty quickly on this example, but can we do it every time? We want to do it every time, and if you want to do that, then we need to put the right infrastructure and right strategy in place and build a culture of automation, or HTE, in our organization to gain the full benefits of automation. And that's what I'm going to talk about. So with regards to HT equipment, we have three main workhorses: a Hamilton MicroStar Lab, which is a liquid handling robot; Quantos Connect, which is a solid weighing robot; and we have Unchained Lab equipment that can do both solid as well as liquid dosing. And we have one big kahuna and two junior units in our department. So all of these equipment come with their own strengths and weaknesses, and we use them appropriately in our workflow. Talking about the workflows. So ligands and catalysts are the languages we speak in. These are our currencies. And currently we have more than 1,000 compounds in our library. So we need a strategy to pick up ligands and catalysts before the screening work. If we started going back and picking and choosing and weighing ligand before every experiment, it'll be too cumbersome, too inefficient, too time consuming. So because of that, we have come up with a system of pre-plates. So for example, we want to screen for a palladium catalyst cross-coupling reactions. So we have identified a collection of 48 ligands that are expected to work in most commonly used cross-coupling reactions, and we plate them twice on a 96 well plate. And when we make these plates, we make 12 to 24 copies at the same time, and we store them in a nitrogen-filled glove box. So when we have to screen for a reaction, we pull a plate out, dose the solid using Quantos and liquid using Hamilton or Unchained Lab, and off we go. So this strategy has been really helpful, and we find solutions for more than 80% of the problems that we face, or at least this approach allows us to zoom into a ligand class that can be further optimized. So given the success of diverse coupling preplate, we have established many other preplates. For example, for copper coupling, CH functionalization, photoredox, and whatnot. Most excitingly, we have also managed to plate enzymes onto 96 well plate using a technology called InZbeats. So the InZbeat technology was developed at AbbVie by Ryan, Jesse, and Noah. And what Ryan, Jesse, and Noah can do is that they mix enzymes on glass beads in an acoustic mixture, and that deposits enzymes on the glass bead. So what it does is that it takes a flocculent, difficult to handle, difficult to weigh enzyme and converts that into a very free flowing, easy to handle solid. And then we dose that solid using a solid weighing robot, and we have found that Quantos Connect is actually the most appropriate robot for dosing that at sub-milligram or 1 to 2 milligram scale level. So on the left of this slide, I'm showing you some PLM images. So the first image is for just the glass bead, and the second and third images are for 5 and 10% loading. As you can see that 5 to 10% loading stick reasonably well to the glass bead. When we go to the fourth picture, 20% loading, the enzymes don't stick well. So in our experience, we have found that 5 to 10% loading, weight by weight percent loading of enzymes on glass bead is appropriate for making InZbeat. On the right, I'm showing you a comparison of 4 different keto reductases in a ketone reduction reaction. And the same enzymes were either dosed as an InZbeat or a hydrated enzyme was compared. As you can see in the overlapping dots on these plots, the InZbeats and hydrated enzymes compare really well. And not just the reactivity, but even the distereoselectivity are very comparable for InZbeats and hydrated enzyme. So I won't have time to show you more examples, but Ryan's paper is out in OPRD, and if you're interested, take a look. I won't be exaggerating if I tell you that the invention and implementation in InZbeats has been a game changer for our biocatalysis workflow and has improved our productivity by leaps and bounds. The other place Quantos Connect comes very handy is for metal scavenger screening. So we also make pre-plates of absorbents. So what we do is that we weight 8 different kinds of carbons and 4 different kinds of silica in 1 gram vials and make 2 copies of that, like so 24 in a collection, and then we make multiple copies of that. So if a process chemist wants to screen for metal removal, they grab a plate, They run their experiment by adding solids and mixing it. They filter it out, and then they analyze the liquor on XRF for residual metal. So having access to reliable and stable equipment along with a very robust workflow have really lowered the bar for doing this tedious yet important work within process chemistry. And this kind of workflow and reliability is helping us improve the HT culture within our organization. Let me give you another example that is helping us build HT culture. So in addition to doing reaction optimization, reaction screening, we also have begun to do reaction optimization in HTE. So for example, a project team was working on this SnAr reaction uh, for a scale up. So the product was found in 93% yield, which is very good, but this dimer impurity, which was very difficult to reject, was formed in 0.6 area percent, which is really high for us. In addition, the reaction conditions were not really suitable for scale-up. For example, a large excess of Unix base, like 15 equivalent, was used that made the workup really challenging. Large excess of reagent B was used, and it's a really expensive component, so you don't want to throw away 70 mole percent of this reagent in every reaction. The reaction temperature of 120 degrees Celsius was really, really high, and we need to lower that to enable a scale-up. So the project team came to us to see if we can help them find a more scalable condition and also to reduce the dimer impurity to less than 0.4% for this project. We also have a preplate for SnAr reaction. So in this preplate, we dose these 16 bases shown here on 96 well plate and make 6 copies of that. That allows us to look at combination of the 16 bases and 6 different solvents. So we pulled one of these plates out and then we screen the reaction. And for screening, we use 1.5 equivalent of expensive reagent B and ran the reaction at 80 degrees Celsius, which is lower than 120 degrees that was being used for the initial conditions. This is the heat map that comes out. Not surprisingly, polar solvents such as DMF, sulfolane, DMSO, and NMP work well in this SnAr reaction. But we were excited to see that inexpensive bases such as potassium carbonate and sodium carbonate worked well across many conditions. So yes, this is an exciting and good lead, but this is not the end of the story, right? Because there are several other parameters that need to be optimized. So for example, which base, potassium carbonate or sodium carbonate, is the optimal base, and whichever is the optimal base, what equivalent of that is optimal? Which of the polar solvents like DMF, sulfolane, NMP, DMSO is optimal for this reaction, and which combination of the solvent and base, an equivalent of base, will be optimal? Can we lower the equivalence of the expensive reagent B? And if yes, then how low can we go? And also, what is the optimal reaction concentration with regards to both the rate of the reaction as well as the impurity profile? So every process chemist has to go through these optimizations, but if you do one experiment at a time, then it will easily require more than a couple of weeks to do these many number of experiments, just given the number of parameters. We thought, can we do it in one night? And we did that. And we did that by starting from a blank 96 well plate, and we dosed the top two row with 1.5 equivalent of potassium carbonate and next with 3 equivalent of potassium carbonate. And we did the same with sodium carbonate. Then we picked the 3 columns on the left and dosed DMF there, and then we dosed other 4 optimal solvents. So here we are looking at combination of 4 solvents and 2 different bases at 2 different equivalents. What we could also do in the same plate, that we can screen 1, 1.5 and 2 equivalent of the expensive reagent across all conditions. And again, since this is 96 well plate, we can do a lot. We could also screen the reactions in the 4 volume or 8 volume across all. So as you can see, every parameter that I talked about in the previous slide can be explored in just one experiment, and that's what we did. Other interesting factor is that only 1.3 gram of material was required for this. We were not material limited, but why waste material when you don't need to use it? So in this experiment, all the solids were weighed using Quantos, and the stock solutions of liquids were added by using Hamilton. So I will not bore you with the heat map for that, but just let me point out, at the end of the experiment, conditions came out that the team was now able to use to scale up to 3 kilogram scale. As you can see, the amounts of the expensive reagent was lowered to 1.07 equivalent from 1.7. the impurity was formed at only 0.2% level. The reaction temperature of 80 degrees Celsius is now much more scalable than 120 degrees Celsius. There is no need to use 15 equivalent of Unix base. That was the problem workup wise. Only 1.07 equivalent of inexpensive base is okay. So essentially we had a scalable condition from only 1.3 gram of substrate. So this kind of workflow and success is really helping us build the HTE and automation culture within our organization. So I will not give you any more example, but my remaining time before Moise comes back, let me talk about our effort in information management. So we really cannot reap the full benefit of automation until we have a system for automated, systematic, error-free data capture that can be easily mined. Right? So I know every company has effort for that, and this is the approach we have taken, and let me walk you through that. So if you look at any HT experiment, there are many steps to doing an HT experiment, correct? For example, identifying what reaction you want to do, designing the experiment, actually conducting the experiment, collecting analytical data, analyzing data, collating data, and finally visualizing the data or reporting that data. Now, many different softwares are used for different parts of these experiments. And as you can imagine, that the sequence of these events is similar to any single experiment, but the complexity is multiplied by a factor of 96 or more. And the thing that makes it even more complicated, that every experimentalist has its own way of using the software and their own way of reporting data. So in addition to data being non-structured and inconsistent, it also requires a lot of time because we have so many different ways of doing things. So on this slide, the length of these bars are our estimate for the amount of time taken for each of these activities. So our goal for information management, in collaboration with our information management team, especially Kushal and Eric, was to reduce the total time taken for information management by at least 50% while generating very consistent and easily searchable data. In order to do that, our first job was to standardize the data flow across different units. So we need to simplify the picture first. So we identified three main buckets of data. These were problem submission, experimental design, and data analysis. And we thought that the visualization and reporting should flow from all these three buckets of data, and the user should not have to worry about that. So we went about standardizing the workflow for each of these buckets and then built a tool that can stitch these three buckets in the background and automatically generate the visualization and reporting in a very consistent, error-free, and structured fashion. We want to do that because we believe that by doing this, this will lead to increased efficiency, better or more robust decision, as well as set us up for more predictive machine learning kind of tools. So let me walk you through our architecture for that. So as I said, there are three major buckets of information: problem submission, design of experiment, and data analysis. And somehow we need to generate the visualization from these buckets. So a lot of things need to happen in the background, as you see from these arrows, but the user doesn't need to be bothered with these arrows. But we still need to build the system in the background where things can be taken care of. So what we do is that we have set up a system where once the problem is submitted, it triggers creation of an experiment in our database that we call Nest database, and that automatically generates an ELN experiment. So once that happens, we go and create design of experiment. That design of experiment goes to the same database and gets attached to the same ELN in an automatic fashion. Users don't have to do anything. And once you conduct the experiment and analyze the data, that data also gets attached to the same ELN automatically. What happens that when database knows that all three buckets of information are available, then it starts generating the visualization, and that also goes and gets automatically attached to the ELN. So let me show you a couple of examples to really show you like how this happens. So our submission page is just a web portal where we require users to provide minimum information such as project name, what kind of reactions we are working on, and a ChemDraw scheme. And all of these names are chosen from drop-down menus and are consistent with our internal ontology. So what happens when the submission page is submitted, then it automatically assigns its experiment number that triggers creation of NERD's ELN. And it also does that it captures the purpose of experiments in an automatic fashion. And it's really important for data mining that the experiment purpose is always written in consistent manner, and then the blue text shown in the slide is automatically populated from the drop downs that we chose from the submission page. So very consistent, error-free purpose of the experiment. Once we have done that, and once we have collected the data, before that, we need to create a design of experiment. So we use LIA, Unchained Lab Software, or ACD Catalyst to design experiments. Now, users have freedom to design experiment the way they prefer, but the output is templated. So you can use LIA the way you want, but the output is always consistent. And once that output file is generated, it goes and gets attached to the NERDS ELN. Same thing happens for data analysis. So we use Chromeleon for data analysis. Again, the users are allowed to use Chromeleon the way they prefer to use, but the final output file is templated and consistent and homogeneous across all experiments. So once the Chromeleon file is generated, it gets attached to the same NERDS ELN file automatically via our database. So what happens at the end, that visualization is instantaneously created as soon as you have problem, DOE file, and experimental design. And this is what it looks like, right? It automatically generates the heat map, and it plots all the output parameters against all input parameters. So our output parameters are product, starting material, and top 5 impurities. And these are all auto plotted, or as in a heat map I've shown here. And then we have a drop down menu in our system where you can choose to see a product, impurity, starting material, and whatnot. If you don't like heat map, you can also have bar charts that are generated. So again, these leads to a lot of gain in efficiencies. People don't have to sit on Excel and keep generating these plots. These are done automatically in the background. Finally, what we have done, that we have also put a slider on the heat map to write the conclusions automatically. So you can set a criteria for success, like more than 80% product and less than 5% of impurity 1 meets my success criteria. And if you do that, then the system goes and passes through the data and populates only those wells that meets the success criteria and lists everything in a tabular format. So again, like, it really takes the burden of data tabulation and visualization away from the users and present data in a very pretty, visually appealing fashion that is helping gain popularity within our department. So that was my last slide before I hand back to Moiz. Just want to say that I hope I was able to convey our work in progress. As I mentioned in the beginning, we are trying to put the right infrastructure and strategy in place so that we can really build a culture of automation in our organization. That's it. Moiz, off to
Okay, thank you, Shashank. So I'll continue with some of the other applications of high throughput experimentation, especially on the solid state chemistry. As you can imagine, on the solid state side also, there is significant opportunity of high throughput experimentation. And some of the applications we have found out, such as polymorph screening, salt and co-crystal screening, organic solvent solubility. I think many companies have those workflows already. And I think there is a significant opportunity to develop such automated solubility platform. And then lastly, crystallization screening, such as screen of various continuous variables. And I think here the platform is very similar to what Shashank has shown, starting from Unchained Lab to execute the experiment. And then we have solid and liquid dosing robots, which Shashank showed. And then we have mostly very, very accurate measurement on dosing of solids. We can do it with this Quantos unit. Where we need less than 10 milligram of solids, and then we can also integrate this whole workflow with a lot of analytical technologies. I think Shashank demonstrated very well on the HPLC side, but then we have PXRD based analytical, which is fully automated. We can have 96 well plate analyzed by PXRD in an automated fashion, and also we can have the PLM images. We have recently integrated our PLM 96 well plate analysis with this Unchained system as well. So that's a fully integrated, and we do have some challenges for sure on the solid state side. It's not as easy as homogeneous system because you have to deal with solids, and both solid and liquid needs to be analyzed. So we do have some challenges on the filtration side. There are a lot of things we are trying to improve that workflow, and also when you need really accurate dosing of the solid, sometimes some milligram may not be as accurate. So we really need to think through how we can enable when you really are challenged with the material availability. Continuing on the solid state side, we have really established our form screening platform with a very high reproducibility and accuracy. And also to assess crystallizability, we have 4-tier crystallization platform. I won't go into the lot of details, but within span of 1 or 2 days, you can execute 300 experiments and get a lot of insights on your form screening, solubility screening, crystallizability, etc. Here I have just shown very briefly one of the workflow on the solid state side. So we have our stock solution, API stock solution, let's say, and now we use the liquid dosing robot to put it into some vials and then evaporate, let's say at 50 degrees C for 2 hours. Then we mix that solids with various types of solvent and co-solvent, and then we heat and hold at 50 degrees C for 2 hours. So that's our master plate, and then we distribute that into various different types of post processing such as evaporation, cooling, and precipitation, where we can analyze those final liquid or slurries using PLM or PXRD. So not everything is established yet. We are still working on establishing various different types of workflows. Here I have listed some of them which are being developed by our solid state chemistry team, such as morphology and crystal habit, pH dependent crystallization development. The new unchained system is enabled with pH measurement in a very small volume. Single crystal growth, I think that can be very challenging when you have to do one experiment at a time. But imagine if you can automate that and then integrate that with in-house PXRD we have, or micro electron diffraction, micro ED technology. And then lastly, all our information management system, which Shashank has shown, is fully application agnostic. Those information management system doesn't just apply on, let's say, catalysis or organic reaction. Same workflow we can use for solid state, and I will show later that same workflow actually we can use in for the Mettler or medium throughput experimentation workflow as well. So that's the beauty of some of these information management tools. So I will move on now from the data, high throughput experimentation to more on to the data rich experimentation capabilities. And here the idea is to develop a sustainable workflow and infrastructure that enables automated process development for late stage process optimization scale up. And we have evaluated various technologies for last few years, and Nate Bennett and Weston lead this team, and we have dedicated members to operate, standardize, and maintain equipment. And after evaluation of many technologies, what we have found is really the Mettler technology is the most robust and it's most flexible, and can really apply onto many applications. We have various reaction sizes here, all the way from 7 mil to 400 mil. We have EasyMax, we have OptiMax, and we have RX10, which provide the same interface using IC data center on, and it allows to use any reactor type you want using custom automation, and then you can integrate with various PAT technologies here. And we found that this is the best option for assessing the scalability. We have various types of PAT technologies here, pH probe, IR probe, easy sampler. We have flow pro. I'll show in the next slide. We have integrated that also with various automation platforms, and just showing one example here on how we can use some of these PAT in a Mettler platform to get further insights and develop our process understanding. So in this case, I've shown the CDI activation on one of our late stage project, and once that activation happens, you make this intermediate, which is acetylimidazoline formation, and then CO2 forms. Now CO2 needs to be removed before we go into the next step using nitrogen pulse. So as you can see that we can really efficiently track these species using PAT. And once we add the further reagent, we see the product formation and the reduction in this acetylimidazoline formation. So these are kind of insights we can really gain and really develop our process understanding very quickly. We also, what we have done is we have these automated platforms, dedicated platforms, which is nothing but all sort of reactor technologies such as EasyMax, fully integrated with various PAT tools such as pH probe, PVM, IR, FBRM. In this case, this particular technology, this particular platform is used for the crystallization and solubility screening. And we have also integrated with FlowPro. It's an automated inline sampling and inline HPLC analysis. These are fixed equipment. These are walk-off friendly, and people can come and do their own experiment and do it in a very data-rich manner. And you can get a lot of insights in a very few experiments. I'm just showing one example where you can really screen the solubility as a function of pH. In this case, we wanted to understand change in the solubility as a function of HCl addition. This is the work done by Serenity, and we can see that as we are adding HCl, the pH is reducing stepwise, and solubility is reducing as well. And after certain HCl addition, the solubility doesn't change, and that's a cutoff we wanted to find out, that what is that HCl addition after which the solubility doesn't change. So again, this is one experiment. You can fully get this kind of data rich experimentation very quickly. So those are some of the really big benefit of the data rich experimentation. So now I will move on to the last part of our presentation, which is custom automation. Now this is something which is unique. We find at AbbVie that not many industry has, or many companies have explored, and we find out that when you don't have such off-the-shelf solution, a lot of those we just talked about, when you really want to rapidly deploy these custom solutions, and which sometimes doesn't fit your exact needs, you really need to gain agility, and sometimes cost can be prohibitive. We feel that we can build those technologies internally, and we have put a team of custom automation engineers, data scientists who can rapidly enable these capabilities and gain efficiencies through high impact and timely solutions. So what is custom automation? Is nothing but tailoring of the hardware and software to meet your objectives, and analyzing workflows to get the largest impact. So this is how usually the meetings go between our automation team and the rest of the organization. We get user requirements, we brainstorm the strategy, how we can automate your workflow, identify the best solution, assemble the system, test and deploy, and we take the full accountability and responsibility of deploying those solutions. And if it doesn't work, we come back, and this happens in an iterative manner. In the next few slides, I will show you some of the examples how this custom automation team has made an impact on some of the quick wins and some of the larger, um, very complex systems. So this is a typical equipment used for these kind of automation profile. So we start with hardware. The hardware can be various process equipment such as pump, wet mill, various types of reactors, and the sensors. The next step is integrating those with the sensors such as temperature probe, pH probe, weighing balance, and conductivity meter. And the data acquisition from these hardware and sensors need to be in automated fashion. So we use various data acquisition systems. And lastly, we want to develop and build controls and visualization using Intel Nuke system, PLCs, laptop, and web-based platforms. And all these equipments are fully integrated by our custom solutions using various coding technologies such as LabVIEW, C Sharp, etc. So I'll go give you 4 examples how we have enabled, starting with a very simple example. In this case, we wanted to develop a controlled, precise pumping over time. You have a Techmina pump and integrated with a Broncos mass flow controller. And we have a data acquisition and data visualization using LabVIEW. And as you can see, using these kind of control system, you can really have a precise dosing. In this case, the set point was 20 ml per minute, and you can really develop these kind of control boxes and deploy those to the rest of the organization in a very fast manner. This is not just limited to uh, liquid dosing, but you can have similar for temperature control, for pH control, and those kind of workflows. The second one is a little bit more complicated. We have developed this automated batch system. So here you can develop the batch process development screening, where you have to do various dosing of various reagents, slurries, solvents. You run your experiments in this batch reactor in an automated fashion, and then once the reaction is completed using as various temperature, various stirring, various reagent and equivalence composition, you pull the slurries or solution and put it into this fraction collector, and you do this experiment in an automated fashion, and you can screen as many experiment condition as you like, but it's running 24 by 7. So we have hardware where we have pumps, balances, and collectors. We have various types of sensors such as temperatures, weighing balance, and you have various data acquisition, data control system, and we have fully automated this system using LabVIEW, and we've deployed this on a web-based platform, so any user can come and run this experiment in a fully remote manner. The third example is a manual tangential flow filtration, where really when a lot of painstaking experiments to do this TFF, to removal of various for the various ADC application and the removal of various small molecules. And here the data spread we saw because of the manual workflow that was really large. So we wanted to get more accuracy in these kind of TFF filtration. So we put together this again automated system using Masterflex pumps, various types of sensors such as temperature, pressure, and conductivity meter, and with similar data acquisition, data controls, and visualization system. And similarly, we have used LabVIEW to run this kind of setup in a fully automated fashion. And again, this was deployed into the web base so that we can run this in a remote manner. And really a lot of accuracy we gain because of these automated systems. And this is the last case study from our end is an automated reactor setup. In this case, it was a drug product solution which was known to chelate metal, and this risk of metal presented in solutions in ppm quantities, and which was leading to change in the color of the solution. So we wanted to assess this effect of various types of metal as a function of various oxygen levels and temperatures. So it was a very complex system, and we wanted to assess these various parameters in a high throughput manner. So we built this three reactor system. We have three batch reactor system where you are changing temperature, various composition, various oxygen, and the metal spike level in an automated fashion. And you are pulling these samples and analyzing in an automated fashion using this colorimeter by Hunter Lab. And these are the different components you have. And this is the flow cell where once the sample is pulled from these three reactor system, you're analyzing this sample in the flow cell, and you're putting the sample back into the system. So it is a continuously running in an iterative manner from one reactor to second reactor to third reactor. And you can get these kind of plots in an automated fashion. Again, we wrote this whole schematic and whole integration in using a LabVIEW, and you can run this 24 by 7, and you can screen many variables. I'm showing just some examples here where we have spiked various types of metals, various temperature effects, and in this case I'm plotting here three different parameters: L star, A star, and B star. So let me just quickly say what is L star is basically running from white to black color region. A star is running from green region to red region, and the B star is running from yellow region to the blue region. And you can see that as a function of various metal spikes, you can see the effect on these three different color region. And what we found was iron basically had the most impact on the color, and we found that that's an element we need to control. Now this whole automated experimentation basically allowed us to develop the control strategy for various parameters on a drug product solution in a rapid manner, and we were able to include this control strategy in our recent filing. So with that, we would conclude our presentation that every organization have broad set of challenges across processes and stages of development. You have to ask the key questions, you need to bring deep insights, and you need to make these fast decisions. And I hope Shashank and I have shown you guys that using these enabling technologies, enabling capabilities with the right culture and right strategy, you can get really your decisions made really fast with a very small investment of resources and the dollar amount. And with that, I would just wrap up where we are going next. We are moving into more rational design and efficient development. Basically, the integration of in silico models and this automation platforms, and how can we run in an iterative manner. So imagine if you have an in silico model with which you can really predict some of the early experiments you need to execute. So use these automation technologies to design experiment, execute the experiment, and get those data in a structured fashion so you can build and refine those models. As Shashank also mentioned, that as we are collecting these structured data, we can really refine and build those models, and those models can be further integrated with in silico prediction. And you have these loops, and as the data is getting larger and larger and in a more structured manner, these models are going to get better and better, and you will have further integration with your automation workflow. That I would like to just thank the automation team. We have various members from our team who have really helped develop these technologies and brought really the right culture in the organization. The information management team, the analytical R&D, and lastly the PRD leadership, who has really supported us to put these ideas into reality. So with that, thank you for your kind attention, and we can take some questions if you have.